Julian Oes, a senior software engineer for Auterion. Thank you.
Thank you, yeah. Thank you, yeah. So I'm generally working on PX4 and MEV SDK. And today I just have like a hands-on session that hopefully everyone here in the room can take something away from, sort of uncovering some hidden things that are actually in the dev guide about SITL, but might not be that you might not be familiar with. I'm going to start off with a picture of me in Switzerland. Point being, I like the outdoors. I like flying drones as well. But at work, every now and then, I also need to sit down, and because I'm lazy and I want to sit down and I don't want to go outside. And of course, there is the reason that development speed is faster if you can do it in simulation right there on your machine, and safer as well, because you can crash many times. Before I go into the SITL tricks, I think most of you are probably familiar with SITL. Just wanted to take a small step back and explain what it is. So software in the loop simulation, you have everything running on your local computer. The simulator on one side, that's generally JMathSim or Gazebo for sort of the common PX4 case, which simulates the world and publishes sensor values, essentially. Sends that to PX4. PX4 does all of its calculations and what it wants to do in that world. And the output at the end is actuator outputs, so motors and servos. And that gets fed back into the simulator that then does sort of the physics, does another step. So now that's sort of the three tricks that I want to get into. Before I go into those, I don't know, who in the room has heard of that lockstep thing for SITL? Okay. What about shell scripting for SITL? Yes, I thought that. Yeah, what about debugging GDB with GDB valgrind or callgrind? Okay, cool, thanks. Let's go lockstep first. So common problems we've seen with SITL in the last years were sort of the CPU load being too high. Let's say you also do some physics simulation, not physics, you do some 3D simulation next to it, or you have your browser open and it does some things. And suddenly you have either PX4 missing samples or you have Gazebo missing samples, and they're sort of out of sync or struggle to keep up. And yeah, a common thing that you see is this timeout, the sensor value missed, sort of cryptic, but what it usually meant is something can't keep up and you're losing samples. And then if those samples sort of go on over too long, then you can get sort of like an interruption, and it can lead to a crash if you're unlucky. So how could we improve that? So how does lockstep work? Basically, the simulator and PX4 now run in lockstep. And what that means is that the simulator sets the time. So it sends sensor values, including a timestamp. And that timestamp then drives PX4. So if no new timestamp is coming, PX4 doesn't do anything. It basically is stuck waiting on the time it's progressing. Once PX4 sends a new actuator output back to, for instance, Gazebo, then the simulator does another step. So they both wait on each other. Sort of one sample goes round and round. Why should you use it? So I'm saying that because it's in 1.9 and I really think it's important. So I'm asking the question, why should I use lockstep? And so, as already mentioned, CPU usage is too high. With lockstep, you're fine. You can run this on some old computer. Not sure about that one. You can now pause. It might have worked before, but right now you're sure that nothing will advance while you inspect what's going on, while you do your debugging. And what we figured is by sort of abstracting the time, there is a bonus to that. You can now run the simulation faster or slower than real time. There we go. Okay, so how to pause, that one's easy. In Gazebo, you got a button. And in JMFSim, you can press P and it stops, and P again, and off you go. How can you speed it up? This is an environment variable, so it's called PX4 sim speed factor. So a factor of 10 means it's going to run up to 10x the time, depending on your machine. So oftentimes I just put in 20, and then my desktop might do 15x, my laptop here might do 5x. And then you do your normal make. Now, Daniel has been working on sort of better VSCode integration. And in there, you can do the same thing. We just got that merged recently, and it's this, the same environment variable, basically, that you set in this tasks.json file. So, let's see if we can demo this. We got QGC with a mission loaded. Now I'm just going to set the speed to 20, as I said. Go as fast as possible. And we're going to use the standard VTOL. Yeah. Okay, there we go. Where's my upload button? Here it is. Okay. Start that mission. Zoom out a bit here. So we're trying to fly from ETH, where we are right now, over to the Auterion headquarters, along Limat, the river, and then. So this is the standard VTOL, and it's going at 16 meters per second. But then, if you look at the real-time factor in Gazebo, right now it's 3. Yeah, 3 to 4. So what we can get on this machine. As I said, up to about 15 on a desktop. I'm sure there is room for improvement. If you find anything, let me know. The model's still there, it's just our camera's not. There it is. Okay, we're there. Now we're just going to descend. Right, and we just covered. Just wanted to check how far that was. Never mind, I believe it was about 3 kilometers that we did in this short time. Cool, let's go back. So, number 2, shell scripting. So you're probably familiar with the not shell, so the shell scripting and init startup on Notix. So it's a great way to sort of interact with the system, to run your custom command, to figure out what can the command even do, or to use it as debugging using top free, these sorts of tools. And turns out we actually have not quite the same, but a very, very similar system for SITL, or for built on POSIX. And all you have to do is add the bin folder in your build directory to your path. And if you look at the ls output, you can see that there's a whole bunch of aliases, symlinks to PX4 with those names. And so that mimics using the PX4 modules as sort of executables, when actually they then get run against the PX4 actual process and just spawning a thread. Looks like I have to demo this, so that's not the one. Let's go here. Okay. So what I want to show is I'm just going to run JMFSim for this. Okay, that's the wrong one. SITL JMFSim. And now I want to interact in the same way as in the nutshell. just need to go into my firmware directory, and I need to add the path as I showed before. So export path down. And I have now, if all goes well, let me do that without the speed up so it's a bit easier to see. Okay. Commander, take off. Oh, I was too early. Yeah. I've seen that one before. There we go. Cool. And just to show the pause thing from before, so I can just go pause and continue again. And now I want to do some inspections. I'm going to do UORP top, so in this case PX4 UORP top. And I nicely, in another terminal, I can sort of look at this diagnostic. And I can do the same thing again. Just need to add the path again. And I can do something like PX4 listener. Let's look at sensor combined 1,000 times. And I get the listener right in some terminal, and I can leave that running. I can grep in there. I can just sort of have more things to debug what's going on. So that's shell scripting. We have seen that. Third one, debugging with GDB, valgrind, and callgrind. I'm not going to cover like how to do GDB, valgrind, or callgrind. I'm just going to sort of quickly say how that's actually quite easily doable with PX4. All you have to do is do underscore the model, so iris or plane, and GDB. That's as easy as it is. And thanks to Daniel's recent work with VSCode, it's even possible out of VSCode. Let's see. No, neither. Here's VSCode. There will be documentation on the VSCode usage. That's work in progress. Just going to make sure that my targets down here are correct. Then I'm clicking on the debug symbol here. And all I have to do is press play and hope for the best. Okay. So that's as usual. So I can do commander takeoff. No, I can't, as usual. Anyway, while we're waiting, I can show you here that all the threads are running. Some of them are nicely named. And I can press pause. And I can go into sensors, and I can check what's actually going on over there. Ignore that one. So in this case, it's waiting on the semaphore. It's waiting because lockstep gives it the next timestamp, and so many threads tend to be waiting on the next time. So anyway, on that, I can just press play, and you've seen that also the local variables were shown. It's just how you would expect it in an IDE. Breakpoints should work as well. Let me try to demo that. So commander demo, boom, and we landed right in here where I set a breakpoint. So welcome to the summit. Yep. Again, that's what you were seeing. Memory detection, memory error detection using valgrind. So valgrind is a great tool to find uninitialized memory, especially at the point when it's used. Find memory leaks, and it's much more powerful than that, but that's just sort of the basics it can cover. I suggest you look at the docs and resort to it if you need it. Again, the usage is actually with PX4 is easy. Just your model underscore valgrind. That's it. And what you get is a lot of verbose output like this. And all this tells you is that some socket call, so you're using data in a socket call that you're sending somewhere, for instance, points to uninitialized bytes. And then it gives you all of the information that might help you in finding where this uninitialized value was initially created, in this case, some EKF function. Just as an example, what you might expect from valgrind. Profiling using callgrind. Callgrind is a tool on top of valgrind, and it gives you profiling. So function call graphs, function call counts, time spent in the functions, and much, much more. So whatever you might need to profile what's going on. And so you can, in my opinion, do a lot of profiling before having to go onto the target, having to go onto the PixHawk and figure it out there. What happens is that you get a dump, a callgrind.out file at the end of the simulation. And you can then use or inspect that data in a tool like kcachegrind is what I like. If we zoom in on the picture here, for instance, that's just a quick SITL run that I did, and I figured more or less that EKF is about using 20% of the CPU time, without further inspecting that, but it seems about in the order that we would expect. And then you can sort of zoom in on all of these functions, looking for whatever information you need. So, okay, what now? I hope I could give you some ideas, some tools in the back of your mind that next time when you're debugging something, you might resort to. And it's all in the dev guide except the VSCode that's ramping up. So just now you have the keywords, look for that, and I'm sure you can find something helpful. And yeah, thank you for your attention.
Wow, who knew debugging could be so fun? Any questions for Julian? Yep. No, go ahead.
First of all, I want your bash prompt. How can I get your bash prompt?
Oh, right. So C shell with oh my set shell.
Okay. Hey,
for set shell with oh my set sh. Yeah.
C shell.
C shell.
Okay.
Set,
Thanks.
Set shell. Yeah.
It looked awesome. There were apparently significant changes between PX4 1.8 and 1.9 SITL setup. Can you maybe elaborate what were changes were? Because everything on my side, everything broke, and I don't use Gazebo. We have our own.
In what respect? In what respect broke?
So first of all, the transport changed from UDP to TCP,
Correct.
and it actually expects, it doesn't bring the TCP server, it says listening on this TCP port, but it actually is talking to that port, and then it complains that after that problem is solved, it complains that the sensor values are stale, even though it does receive them. So,
yeah, I probably can't give you the solutions now for all the things that changed. What I can say, yes, we went from UDP to TCP because with UDP potentially, if you run the simulation on one side and then PX4 on another host, you could lose on the networking, you could lose packets. So we had to add TCP. Now, if that broke your simulation setup, which might be different, UDP is still an option. We didn't delete UDP, so to say. So you can, with some setting options, go back to UDP. You can also go back to non-lockstep. So
is it the only two major things that changed?
Pardon?
Lockstep and TCP, is that the only two major changes to your knowledge?
There was also changes to the shell implementation, so how those things talk to each other. And there was many more changes that I'm probably not aware of right now. So
Okay,
I guess
thank you.
look at the changelog and the diff and approach me for anything with lockstep that you're stuck with, like to all of you. That there have been several things coming up, and every now and then my answer was you can try without lockstep, sort of go to the previous behavior, or you can implement a new thing, but it takes some, you need to make sure to adhere to the lockstepping, otherwise you will just stall.
Any more questions? No? Well, thank you, Julian, for your time.
Sure.